section 13.8 was on arc length, and I thought I would just do problem 43 with you. Number 43 is one a few people asked about. Oh, okay. So it just says R of t is equal to the vector t comma 2t for 0 less than or equal to t less than or equal to 3, right? Determine whether this curve uses arc length as a parameter, and if not, find a description that will use arc length as a parameter, all right? But by the way, what kind of curve is this? Well, it's in R2, right? I suppose I could plot it. Let me do that. I mean, this, it's looking linear to me, right? I mean, if I put in a 0, I'm at 0, 0. If I put in a 1, I'm at 1, comma 2. If I put in a 2, I'm at 2, comma 4. And if I put in a 3, I'm at 3, comma 6. So that's my curve. This would be a bad example for tonight's homework, right? No curvature. But maybe it's a good example for arc length. Is this an arc length parameterization? That's really the question. So we had a formula that I want to recall. Do I have it up here? No. Do I dare? Yeah, I dare. Here we go. 13.8. Arc length as a parameter. And there's a few examples here, but the arc length function, they say, is this s of t, right? So I'd like to compute the arc length function for this example, because they say s of t is equal to the integral, and this is where you go from a to t, right? So from a to t, and this is where I use a different letter than the book uses. Looks like they used mu. I'm going to use tau. V of, they're using u. I don't like that so much. So let's say the absolute value of v of t. We can't use t because it's already taken, so I'll use tau d tau. How about that? You can use whatever variable you want, I guess. So let me go ahead and try to compute that here. So if r of t is given by this, I could compute r prime of t, right? So that would be 1, comma 2. Well, there we go. That's kind of nice. And next, I want the magnitude, because v of tau is the magnitude of r prime of tau. And so that's the square root of this guy squared plus this guy squared, so 1 squared plus 2 squared. So the velocity, it says, is always the square root of 5. Right? And that doesn't matter what t is at all. V of t is the square root of 5. So I guess the magnitude of v of t is also the square root of 5. Okay, so let me go back to this arc length formula and see if I can use it now. So s of t would be the integral from 0 to t. I'm choosing 0 because that's kind of the starting point of, well, the square root of 5 d tau. And so I'm getting the square root of 5 times tau from 0 to t. And so I'm getting that s of t is the square root of 5 t. Okay? And so now this is kind of interesting, I think, because then you could say, well, t is actually 1 over the square root of 5 times s. Right? Or if I keep it this way, arc length is the square root of 5 times t. This parameter t that I'm using, you could say it's faster than the arc length parameterization. How much faster? Well, take the arc length parameterization, multiply by 1 over the square root of 5, and that's the speed I'm going. So I guess that would be my answer to the question. Let's look at the problem one more time and see exactly how it asks it. It says, determine whether it uses arc length. If not, find a description that uses arc length as a parameter. So I guess if I want to write R of S, and as soon as you write S, you're saying, hey guys, this is parameterized by arc length. I need to take t and replace it with 1 over the square root of 5s. So it would be 1 over the square root of 5 times s, comma, and then, 2 over square root of 5s, because I replaced that t with the same thing. Or I could say 1 over the square root of 5s, comma, 2s. Is that the answer they had, guys, for this one? Say it again. That's a good point. We have to also give what are the boundaries on the parameter. So I guess I would say that S should be between 0 and what is it? 3 radical 5, right? Because if I take 3 radical 5 and plug it in, it cancels and you get what you want. Yes? So that's a good point. That's a nice exercise. I mean, it kind of gives you this idea that, oh yeah, when we say we're moving with respect, we're parameterizing by arc length, we're actually moving at a certain speed. And I think that's hard to understand, but the calculation shows it. It shows that, oh, here's a very simple parameterization for this line, but somehow this is too fast. If you want to do things like talk about curvature, which we just defined as being dt ds, then you need things like this. So, yeah, I think that's worth doing from last night.